All right, guys, in this lesson, we're going to be looking at chi-squared tests for homogeneity. So our objective here is just to compare conditional distributions for data in a two-way table. We also want to state appropriate hypotheses and expected counts for data in a two-way table. We then want to calculate the statistic, degrees of freedom, and p-value for a chi-squared test based on a two-way table instead of a one-way table. And we want to perform a chi-squared test for homogeneity. So, a couple things to note, just some review from the last lesson that we looked at. We really looked at a chi-squared test for goodness of fit, which again is a hypothesis test to see if a sampling distribution matches a known population distribution. In this case, we really only used a one-way table, so now we're going to add another element to the chi-squared test that basically concerns a two-way table. So again, a two-way table compares two or more categorical variables among individuals in a population. And we have two terms that we really need to understand when looking at a two-way table. We need to understand what marginal distributions are, which those compare the outcomes among the individuals in a distribution. Marginal distributions are going to be the row values or concern the row totals, basically. So again, when you think of marginal, you think of the word margin, and when I think of the word margin, I think of the totals columns in my two-way table, basically. Our conditional distributions is our second term we need to understand, and that's just comparing the outcome of each variable among the individuals in a distribution. This is going to be concerned more with individual cell values as opposed to actual total values, basically. So those are two terms we kind of need to understand when solving some of these problems for chi-squared tests. And then the two chi-squared tests that we're looking at that concern two-way tables are going to be our chi-squared test for homogeneity, which is a hypothesis test to determine if the distribution of a categorical variable is the same for each of several populations or treatments. And then we're also going to look at chi-squared test for independence, which is a hypothesis test to determine if there is an association between a row and column variables in a two-way table. We're really going to be looking at chi-squared tests for independence in the next lesson. In this lesson, we're really only focusing on chi-squared tests for homogeneity. But both of those tests concern two-way tables, basically. So let's take a look at this example. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a European restaurant compared 3 randomly assigned treatments where no music, French accordion music, and Italian string music were played at the restaurant, and then under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. Here's a table that summarizes that data. So this list, each column represents the type of music that was played in that restaurant, and then the rows will represent what entree was actually ordered based off of what type of music. So in this case, when no music was played, there were 30 French entrees ordered, and when no music was played, there were 11 Italian entrees ordered, and then there were 43 other entrees ordered when no music was played. So really, we have 3 parts to this problem. Our first part is to calculate the conditional distribution in proportions of entrees ordered for each treatment. So again, we know that conditional distributions are really concerning cell values and not totals for our row, basically. So what we're essentially trying to find for conditional distributions is we're taking whatever's in cell 1 when no music is played and a French entree is ordered, divided by the total in that particular column. So that's going to give us, at that point in time, we have about a 36% distribution of people who ordered French food when no music was played, about a 13% distribution of people who ordered Italian food when no music was played, and a 51% distribution of people who ordered other food when no music was played. We also know that we have a 52% distribution of people who ordered French food when French music was played, and then kind of so on and so forth. So that gives us, really we're just taking whatever's in each individual cell, 30 divided by its column total, or 39 divided by 75, or 30 divided by 84, right there. Part B of this problem says to make an appropriate graph for comparing the conditional distributions in Part A. So essentially all we're doing is we're graphing the data that we found in Part A of this problem. So I know that it was about 36% who ordered French food when no music was played, about 13% who ordered Italian food when no music was played, and then about 51% who ordered other food when no music was played. So you can just make that by simply making a bar graph for each one of those distributions. Finally, Part C asks us to write a few sentences comparing the distributions of entrees ordered under the 3 music treatments. And this is where the actual chi-squared test really comes into play. So this is where you have to go through that 4-step process again. So when we're stating our hypotheses in the first part of our process, our null hypothesis is pretty much always going to be that there is no difference in the distribution of outcomes among the treatments. That's basically when you're stating hypotheses for this particular test, your null hypothesis is always going to be that there's no difference, and your alternate hypothesis would be that there is some difference in the distribution of outcomes among the treatments. In our restaurant example, we would say that our null hypothesis is that there is no difference in the type of entree ordered based on the type of music playing, whereas our alternate hypothesis is that there is a difference in the type of entree ordered based on the type of music played. And the purpose of our chi-squared test is one of multiple comparisons. So since there are 3 outcomes with 3 treatments, we will have to test all 9 results to see if there is a difference at all. And we will test all the results at one time to see if there's a difference in the outcome. Now, in order for us to test all 9 of those results, we have to know the expected value for each one of those 9 scenarios, basically. Now, how you find the expected value is basically this formula. So we will base our expected counts on the total numbers of each outcome for each variable if the null were true. And so what we need to do to find that expected count is we need to take the row total times the column total and divide it by the table total. So when we're looking at expected counts for each one of these scenarios, which again, a scenario is French entree being ordered when no music is playing, an Italian entree ordered when no music is playing. All that represents 2 separate outcomes that could have happened, basically. So, excuse me. We would need to take our row total times our column total and divide it by our table total. So 99 times 84 divided by 243 is going to give us an expected count of about 34.22. We would do the same thing for Italian. 31 times 84 divided by 243. That's going to give us a value of 10.72. We would do it again. 113 times 84 divided by 243. That gives us a total, or an expected count of 39.06 for this. We would do the same thing going through each one of the other scenarios in this case to find our expected count for everything. And that leads to actually finding the test statistic in this case. Once we have stated our problem, we need to make sure that we check our conditions for the plan portion of the 4-step process. So we need to check to see if it's random. The data must come from an independent random samples or from the groups in a randomized experiment. It must meet the 10% condition to be independent. So when sampling without replacement, we want to check that the total number in the sample is less than 10% of the total population. In this case, they told us in the problem that it was a random sample. We can probably say that 243 total people that were tested in this are going to be less than 10% of the total number in the restaurant. And then our large counts condition must be met as well. And so all expected counts must be at least 5. So we know that when we're looking at this, 34.22 is less than 5. All of these values that we found, our expected values, must be less than 5 in this scenario, okay? So from there, we can then find our test statistic, or our chi-squared statistic, and then our p-value as well. So from this, in order to find a chi-squared statistic the long hand-drawn way, it's going to be the observed minus the expected squared divided by the expected. And so if we were to do this the super long way, we would take 30 minus 34.22 squared divided by 34.22. Then we would add plus 39 minus 30.56 squared divided by 30.56 squared, plus 30 minus 34.22 squared divided by 34.22, so on and so forth until we get to the end, and that would give us a chi-squared statistic of 18.28. If we wanted to find our degrees of freedom, or if we're asked to find our degrees of freedom, since the data is a two-way table, it's going to be row minus 1 times column minus 1. So we have 3 rows and 3 columns, so it would be 3 minus 1 times 3 minus 1, which is 2 times 2. That gives us a degrees of freedom of 4. So that's how we would find that, kind of the longer way. Now, as always, there's a much simpler way to solve this in the calculator, but it's a little different than what we're used to as far as this. So we have to enter in our values in a matrix, basically. And how we do that is we go to second matrix, and your matrix button is actually going to be the button just to the left of your sign button on a TI-84. So it's going to be second matrix, and then from there you want to arrow over to edit. So arrow over to edit, and then find matrix A and select matrix A. And then from that, what you want to do is you want to enter in all of your values for matrix A, all of your observed values for matrix A. So just 30, 39, 30, so what they give you in the table, basically. You don't have to enter in all of your expected values because the calculator is actually fairly smart, and it's going to understand that when you go, again, to actually run this chi-squared test, which again is going to be in stat, and then arrow over to tests, and then scroll, you might arrow up to go to the bottom of the list and find C where the chi-squared test actually is. Once you have entered in the observed matrix of A right here, the expected matrix of B will basically automatically fill in all of the expected values. And so once you've entered in everything for matrix A, just go to your chi-squared test, arrow down to calculate, and it should give you your chi-squared value of 18.28 with a p-value of 0.0011 and a degrees of freedom of 4. If you wanted to draw this graph, all you would need to do is, again, go to the chi-squared test, and instead of hitting calculate, just hit draw right there, and you should be able to get your graph right there. And then if you wanted to know the expected values for each one of the values that you entered in for the matrix, all you would need to do is, once you've run your chi-squared test, then go back to second matrix and edit. But instead of selecting A, you would select B, and what it's going to give you is it's actually going to give you all of the expected values that you should have for that. So that's where, once you've run your chi-squared test, that's where matrix B is automatically filled in with all of the expected values based off of the observed values that you entered in for matrix A at that point. So it's actually kind of a neat way to figure all of that out and to make your life a heck of a lot easier. So again, our chi-squared statistic in this problem was 18.28 with the degrees of freedom at 4 and a p-value at 0.0011. So if we were asked to interpret our p-value in words, it would be if there's no difference in the type of entree ordered based on the type of music played. In other words, if our null hypothesis is true, then there is only an 0.11% chance that we would see the level of difference or greater in the orders during other samples of this size. So because our p-value is less than a significance level at 0.05, we would reject the null hypothesis and say that there is convincing evidence to believe that there is a difference in the type of entree ordered based on the type of music playing. So again, this is an interpretation of the p-value. If they ask you to interpret the p-value, you say, if the null hypothesis were true, there is a p-values % chance that we would see what we see in the sample. And then if we're asked to just conclude our problem at the end of the 4-step process, we would say, we would compare our p-value with our significance level. So since that p-value is less than our significance level, we reject the null hypothesis and say that there's convincing evidence to believe whatever the alternate is in that case. So again, a couple things to note for chi-squared tests for homogeneity. Your hypotheses should be basically the same. There's no difference for your null hypothesis, and then there is a difference in your alternate hypothesis. You want to make sure that when you are calculating the test statistic or the chi-squared statistic, it's always going to be epsilon of the observed minus the expected squared divided by the expected. But again, there's a super much easier way to find that in the calculator. And then if you're finding the degrees of freedom, it's always going to be the number of rows minus 1 times the number of columns minus 1. And the p-value is always going to be the area to the right of your chi-squared statistic under the corresponding chi-squared density curve. So in other words, what that means is that I would find where my chi-squared statistic is on this curve, and my p-value represents the area to the right of that chi-squared statistic under that curve, basically. So that's what we're looking at when it comes to that. Now let's look at one more example for this kind of stuff. So random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differ from those of people who have landline service, the poll results may not represent the entire adult population. The Pew Research Center interviewed separate random samples of cell-only and landline telephone users who were less than 30 years old. Here's what the Pew survey found out about how these people describe their political party affiliation. So again, we have a two-way table where they interview those who only have a cell phone and those who only have a landline phone, and they basically determine whether or not they are Democratic or lean Democratic, Republican or lean Republican, or they are independent and refuse to lean either way. So if we wanted to run a chi-squared statistic for homogeneity, we want to say, does this data provide convincing evidence that at a 5% significance level, that the distribution of party affiliation differs in the under 30 cell-only users and landline users? So again, we would go to second matrix, arrow over to edit, select matrix A, and we would enter in all of our data from that particular table, which again, we're not counting our total values here, so it would only be a 3x2 matrix and not a 4x2 matrix in this case. So we would enter in all of our observed values, then we would go to stat, arrow over to tests, find our chi-squared statistic test, and we would enter in matrix A for the observed values. Matrix B would still be there for the expected values. We would hit calculate. That would give us a chi-squared statistic of 3.2199 with a p-value of 0.199 and a degrees of freedom of 2. And if we wanted to find our expected values for based on our observed values, we could just go back to second matrix, arrow over to edit, find matrix B, and we would see our expected values listed right there. So again, if we're asked to run a test on this, if we're asked to prove whatever it is we need to prove based on our chi-squared test, we actually have to run the entire test. So again, we want to state right here, and our parameter is the distribution of political affiliation between the different phone users. And then we also need to state our null and alternate hypothesis. Our null hypothesis is that there is no difference in the distribution of party affiliation of cell-only users and landline users. And then our alternate hypothesis is that there is a difference in the distribution of party affiliation of cell-only users and landline users. From there, we would need to plan. So we would need to check to make sure that it is random. We are told that the samples are random. We need to make sure that the people in our sample represent less than 10% of the total number of each one of those users. So we want to make sure that both 96 and 104 is less than 10% of the total number of cell users and the total number of landline users, which it does. And then since all the expected counts, if we see the screenshot right here, we'll note that all of the expected counts in this case were above 5. Then that large counts condition is met, so we're good with that. Then from there, we would need to perform the do portion, which we already did based off of all of the work that our calculator did for us, but you want to make sure that you list in the do portion that you ran a chi-squared test for homogeneity. And that gave us all of our values, and then list your chi-squared value of, what was it, 3.22 with a p-value of 0.1. This one it'd probably be about 0.200, and then a degrees of freedom of 2. And then we would check to see, since 0.1999 is greater than 0.05, we would fail to reject the null hypothesis, and there's not convincing evidence to believe that there is a difference in the distribution of party affiliation between under 30 cell only users and landline users, and that represents our conclude portion. And so you need to make sure that you have all 4 of those parts listed out in order to receive full credit for those particular problems.